All right, the final Praat demonstration here is going to be of the independence of source and filter. So I'm opening my Praat program. I'm going to get rid of the picture window because we're not using that. And then I'm going to open my files. The files here, I'm going to go navigate to them. We're looking for the source filter audio. So I'm just going to select everything in this directory. Although actually one of these won't play in Praat. And I'm going to open them. One of these is a music file that just won't open in Praat. Oh, and it didn't open the others either. Okay, let me try this. Uh, don't open that first file, just these ones. Okay, cool. So here I've got my files. I'm going to want to view and edit them. And so here's what we're going to do for the source and filter demonstration here. I've been telling you that the source properties are completely independent of the filter properties in acoustic terms. And in linguistic terms, these correspond to different kinds of phonetic and phonological dimensions of contrast. And so I'm going to try to demonstrate this here by changing the source properties without changing the filter, changing the filter properties without changing the source, and then changing both of them together. Right? And the sort of point, the overarching point of this demonstration is that we can actually hear each of these things in very different terms. So when you only change the source, it has a different perceptual effect, auditory effect, than when you only change the filter. And those are both different from when you change the filter and the source at the same time. Now, for each of these comparisons, there's a sort of normal, unspectacular way of demonstrating it with normal linguistic stuff. And I'm going to show you some sort of funny and interesting ways of demonstrating it by manipulating natural speech and making artificial sounds. So for the first one here, we're talking about changing the source properties without changing the filter. In linguistic terms, that would correspond to changing some properties of voicing or F0 without changing the quality of the sound. Right? And the sort of simple, not too exciting illustration of this is that whether I say dog or dog, it means the same thing in English, right? So the pitch, the intonation, the F0 changes there from low to high, but the segments, the d, the ah, and the g, the features, it's still a low back unrounded vowel, right? So the filter properties are not changing. Now, in many other languages, changing the F0 in and of itself would change the meaning of the word. These are tone languages. English happens not to work that way, but the point is, even in a tone language, you can change the tone of a word without changing any of its segmental features, right? So you could, in Mandarin Chinese, famously, there's like a minimal quadruplet of words with the segmental form ma, but if you change just the F0 of it in different ways, it becomes four different words in Mandarin. It's like, I think, water, mother, hemp, and another one that I don't quite remember. But yeah, so that's the sort of unspectacular illustration. Here's a more artificial one that's kind of interesting. This is just audio of me saying a word.
Grown, grown, grown.
Okay, and we can all understand that as a particular word of English. Here I've taken the exact same recording and doubled the F0.
Grown, grown, grown.
So that certainly sounds different, right? It's higher pitched, yet the characteristics of the segments in here, gr, o, and n, stays exactly the same. The filter properties are the same. It's only the F0 that's changed. It's still, a syllable with four sounds in it. The vowel is a mid-back rounded vowel. It ends in a coronal nasal. So all of these spectral properties, the filter properties are the same. It's only the pitch that's changed. Here we can actually check this. I'm going to go into the pitch menu, show pitch. And let's take a look. Well, let me see how this works in this one as well, because the pitch tracker sometimes has a little trouble tracking very artificial things. Okay, this looks pretty good. So the sort of peak pitch in the O vowel here is going to be around 165 hertz. If you put your cursor here, it will tell you the F0 at that point. And in this one, if I again go to the peak pitch here, it's going to be roughly double, 314 hertz. So the F0 has definitely changed here. The pitch has changed. What about the filter properties, the formants? Let's track those for a second. Ooh, having a little trouble tracking the formants in that recording. Yeah, a little trouble here too. I'm going to change the formant settings and try to get better formants. I'm looking over here and the formants are sort of jumping all over the place, and that makes me nervous. So I'm going to try to get better formant measurements by changing the settings. Maybe the first thing I'm going to try here is adding an extra formant and see if that helps. Yeah, that looks a little bit better, at least down here in this stretch. We're getting the first two formants and probably the third pretty well here. So I'm going to leave that for the time being. How does it do with this one? I'm going to again change this to look for a sixth formant and see how that does. Oh yeah, that looks pretty good. All right, I'm going to leave it the settings like that with 6 formants in each of these, because now I'm getting a pretty clear picture of F1 and F2 and F3. So let's try to do this like right in the middle of the O vowel.
Groan, groan.
Actually, it's more like in the middle of the R, but this looks like a good spot, so I'm going to keep it there, and then we should get it right at the same time point over here, maybe somewhere like around here.
Groan. Groan.
So it's at 194, 198. Okay. Let's check the formants now. So show me all the formants you got for the doubled pitch one. F1, 340, F2, 1120. And what if we look at the original? F1, 400, F2, 1140. So a little bit different in the two because we're measuring the formants a little bit differently, but not grossly different in the two files. We've changed the source. It didn't do anything to the filter. We still have this row sequence in both sounds. Right? So that has a particular sound to it. Maybe it makes my voice sound more like a stereotypically female one or something like that. But keep in mind that auditory phenomenon because it's going to be very different than what happens when we change the filter without changing the source. So how do you do that? Here's one way that this happens a fair bit. Here's ordinary speech.
This is my voice in ordinary air.
How about this?
This is my voice with a vocal tract full of helium.
This is helium that's in balloons that stay up. They're often filled with helium gas, and if you pop one of those balloons and inhale the helium, it does this funny thing to your voice. And people tend to think when they hear this, oh, it makes your voice high-pitched. That is not what's happening at all, though. So check this out. I'm going to open these two files. Here is the normal voice again.
Listen carefully to get the idea of this pitch.
Here's helium.
The voice is different, but the pitch remains the same.
So even though we tend to think of helium speech as being high-pitched, what this is trying to show is that the pitch itself has not, in fact, changed. Let me get rid of the formants in here, just because they're so messy. Here's what we're seeing. So the pitch on this first note, this is going to be the ah note, is roughly 118 hertz. And if we go to the same point in this file, it's about 120 hertz. This is the same musical note. It's the same pitch. It's the same roughly F0. Yet the two voices sound completely different. What's going on with helium?
Listen carefully to get the idea of this pitch.
The voice is different, but the pitch remains the same.
Well, it's not altering the speed at which the glottis is moving. It's not altering the F0. It's altering the resonant frequencies of your vocal tract. So check this out. Let's show the formants here. That looks pretty decent for an ah vowel. I'll keep that for the moment. Try it here again. Ooh, that's much messier. I'm going to change these settings. It's finding way too many formants there, so I'm going to lower the number of formants it's looking for. There's all this mess of red dots all over here in the middle of the ah vowel. That shows that it's finding formants that aren't there. I'm going to go down to 4. That looks a little bit better. Maybe I'll keep that for now. Okay, so here we are in the ah vowel. Here's what the formants, let me do normal speech first. We're in the middle of the ah vowel. What the formants look like in here. Let me get this away from these stray dots over here. Don't want those to mess up the measurement. F1, 600. F2, about 1,000. That's normal speech. Same vowel, helium speech. F1, 900. F2, 1,500. So it's like about 1.5 times as high, the frequencies of these formants in the helium speech, even though the F0 is exactly the same, right? So here we've changed the filter without changing the source. And while people tend to think of this as high-pitched, I think if you consider carefully, you'll realize that this difference,
Groan. Groan.
which really is pitch, sounds very different than this difference.
This is my voice in ordinary air.
This is my voice with a vocal tract full of helium.
Helium speech is different than high-pitched speech, and you can hear it. It doesn't sound like the same thing. Quick bonus question for the physics buffs out there. Why does helium change the resonant frequencies in your vocal tract? This is a very tricky, tough question. Take a minute and try to see if you can think of the answer. Okay, here it is. It changes the resonant frequencies in your vocal tract because it changes the speed of sound in your vocal tract. That is, the speed at which pressure waves can travel through your vocal tract. Why is that? Well, under normal circumstances, your vocal tract is full of basically whatever air is in our atmosphere, and the speed of sound in our atmosphere is about 350 meters per second, and that's how fast sound waves propagate through your vocal tract. Now, helium is one of the lightest chemical elements. It's the second element in the periodic table, and so it's not very dense. Right? If you fill your vocal tract partially with helium, it's going to mean that the medium inside your vocal tract is less dense. It has fewer particles in it, or fewer units of mass per area. And what that means is that things are going to propagate through it faster because there's less sort of stuff to run into along the way. So what you're actually doing when you inhale helium is changing the speed of sound in your vocal tract. And that's why it changes how the waves resonate, or how pressure travels through or propagates through your vocal tract, but it doesn't change the physical property of how your glottis is vibrating. The helium doesn't have any mechanical effect on the source, it only changes the filter. Now, the completely unexciting and everyday boring version of changing the filter without changing the source would just be, for instance, changing from one vowel to another without changing the F0 or the pitch of that vowel. So, o, ah, o, same pitch, different vowel quality. I'm changing the filter, but not the source. You can even do this on a musical note if you want to be sure that you're not changing the F0. A musical note is basically defined by its F0. So I can say E, ah, o, oo, and those are all going to have the same F0, but they'll have different filter properties, different resonances. Okay, last bit here. What if we change the F0 and the resonant frequencies, the source and the filter at the same time? Well, we've heard high-pitched speech, we've heard helium speech. What if you change both things at the same time? It's going to create a third effect that's perceptually, auditorily different than the first two.
This is me at normal speed.
Here's what happens when you change both the F0 and all of the resonant frequencies by doubling the speed.
This is me, but not at normal speed. This is me, but not at normal speed.
All right, so there it is. And this is labeled CHIP, and that stands for chipmunk speech. what do I mean by that? Well, if you're from my generation, roughly, this is going to sound most familiar to you from a cartoon called Alvin and the Chipmunks, where they recorded the voice of cartoon chipmunks by taking an actual cassette tape and just doubling the speed of it. They had actors speak really slowly, and they doubled the speed of the tape, and it comes out sounding like chipmunk speech.
This is me, but not at normal speed.
Right? So here, unlike the other examples, you'll be able to see that both the pitch and the resonant frequencies have changed. So let's pick a point that's comparable here.
This is me, but not at normal speed.
Let's try me. And are we getting decent formant readings there? I'm going to change that up a little bit. I think we need one more formant because I'm seeing it not really picking out the second and third formants very well here. I think it needs more dots, so I'm going to try 5. Oops. Let's see here. Oh, actually, that does not look great either. If we do even more. No, that's a mess. Maybe I'll go back to the 4. Yeah, that's about as good as we're going to get, it looks like. Maybe I'll keep that. And then over here, again, me.
This is me.
This is me.
So we're at a similar point in the sentence here. Formants look much cleaner in this one. Here's the original. We have a pitch here of about 102 hertz. Over here, the pitch is 232 hertz, so more than twice as high. And the formants here, in the middle of an E vowel, are roughly 300 and 2200 for F1 and F2. If we look over here, it's going to be not tracking perfectly, but close enough. 700 and 3200, so much higher formants. Both the source and the filter are shifting. And the observation here is that chipmunk speech sounds different from helium speech, where only the filter is changed, and different from high-pitched speech, where only the source is changed. So your ears are able to separate source and filter, and your linguistic system is also able to separate source and filter. In particular, the normal version of changing source and filter at the same time would simply be 2 different vowels on different pitches. And this would be typical of a 2-syllable word in English, like chipmunk. So we had it, And so there's going to be both different formants in those 2 vowels, as well as different F-zeros in those 2 vowels. And so in linguistic terms, we can clearly distinguish between source contrasts and filter contrasts. In auditory terms, even with these sort of unusual artificial manipulations of the acoustics, we can still distinguish between changing the source, changing the filter, and changing both of them. And in acoustic terms, as we've been looking at in Praat during this video, we can see that acoustically they can be measured independently and they can vary independently. That's the independence of source and filter.